about the project and results which are very important to me. And even if the negotiations are quite advanced now, are giving even further arguments to our negotiators to really limit our emissions. Because what I'm going to talk about today is I'm going to put a nice cost to our CO2 emissions and other greenhouse gas emissions by computing the amount of ice that we lose every time we emit greenhouse gases in the atmosphere. So glaciers are already melting, and this at an accelerated pace. So right now they are losing about 300 gigaton per year that are water system and into the ocean. So to put this into perspective, that's each year that's about 30 centimeters of water which are covering the entire of Egypt and are reaching the oceans. Glaciers are therefore currently the most important cryospheric component to sea level rise, and they will continue to be so in the near future. And they are affecting downstream water availability. So now we are going to look at what happens to glacier ice depending on how much we emit in the future. And so what we have done is that we have looked at possible future climate scenarios, which are synthetic and stylized according to the current rate of emission. So here on the y-axis, you have emissions per year in gigaton CO2 equivalent per year. And they are rising at the level which is currently observing. And then we said, okay, what happens if we start reducing our emissions in 2020, if we start reducing our emissions in 2025 up to 2050? So that's the first part of these synthetic experiments. Every 5 years, we start reducing. And then we also varied the emission reduction rates at rates which are more or less seen into the literature between a relatively slow emission reduction rate of 0.3 gigaton per year, 0.5, and then a very stringent emission reduction rate of 0.5, 0.7 gigaton per year, each year of reduction, so to say. And so this gives us a very long suite of different climate scenarios. And then we have a final separation of the scenarios between the left-hand side, which is a world where we reach a new world which is called net zero CO2. In this world, we stop emitting CO2 emissions, but we still emit other greenhouse gases, such as methane via agriculture or heavy industry. On the right-hand side, we reach a world where we have a true net zero greenhouse gas emissions. So we don't emit any CO2 and any other greenhouse gases. And because we know already that it's going to be impossible to reach entirely, because we are still going to be reliant on emission from agriculture in the future, this world is very heavily relying on negative CO2 emissions. So this is a technique which we call CO2 removal, where we are going to actively remove CO2 from the atmosphere, either by direct air capture, which is a technological solution, or by, for example, planting trees and other vegetation that we are then going to put to the ground. So these are called negative CO2 emissions. Can you remove the warning in the back? Can you remove the warning? Thank you. Okay, so to put this into context, maybe to understand a little bit the difference between these two, this is something which has been discussed also in the very recent emissions gap report from the UNEP, where they have classified countries according to their net zero pledges, because some countries have a very clear net zero greenhouse gas pledge, and this is the case for the European Union, this is the case for Japan, where countries have really said what we want is a true net zero by 2040 or 2050. Other countries, the majority of the countries actually have an unclear net zero target. It's not clear if they want to reach net zero CO2 or net zero greenhouse gases. And so in our scenarios, we are then encompass these two possibilities, the optimum being net zero greenhouse gases. Okay, so you remember these scenarios now. And then these scenarios are then used to project what's going to happen to the global temperature. And so this is the same now, but the response of the climate system according to these emissions. So we encompass a range of possible futures somewhere between 1.5 degree to 2.5 or almost 3 degrees of warming. So this is more or less, if you think about this pavilion here, the range between the most optimistic scenario, which we want to achieve as much as possible, and the current NDCs, so the current policy scenarios, so to say, if states are actually following what they said in the texts. And so if we reach net zero at some point in between now and 2100, temperature are going to stabilize. In a world where we still emit CO2, no, sorry, where we still emit other greenhouse gases. We don't emit CO2, but we still emit greenhouse gases. The left side of this graph, emissions, our temperatures are going to stabilize because we have a residual warming from emissions, but also cooling from ocean uptake of CO2 and of heat. And only in a world where we reach a true net zero greenhouse gas, so no other CO2 emission, no remaining greenhouse gas emissions, then what we are going to observe is a decline of global temperature. Basically, we are going back to pre-industrial at a very, very slow pace. You see that it's going to take centuries to even lose a few degrees of, a few, not fraction of degrees of warming, so to say. All right. So these are global temperature now. And so what we are actually interested in is what's going to happen to our mountain glaciers. And so by mountain glaciers, I mean all the glaciers outside of the big ice sheets. So all the ice bodies which are found on mountains on the periphery of the large ice sheets. And we use a glacier model to simulate their future. The 200,000 of them individually are simulated then with a glacier evolution model. So let's jump to the global glacier response in these scenarios, which is what we are really, really interested in. The outcome, again, on the left-hand side, the net zero CO2, and on the right-hand side, the net zero greenhouse gas scenarios. And this is one of the main results and one of the main outcome of this study is that by 2300, glaciers are still going to continue to melt no matter what. Only in the very most stringent scenario where we stop emitting now, today, and we reduce our emissions at a very high rate of 0.7, glaciers are going to more or less stabilize. We can also classify then the outcome according to temperature targets, which is maybe the most common way that we have done in the past. And also in this pavilion, we are actually classifying the scenarios according to temperature. You can see that the 2 degrees scenarios, which are guaranteeing to stay below 2 degrees by 66% probability, guarantee an outcome about between 40% and 50% of total volume loss, maybe a bit more than 50%. But if we don't manage to stay below 2 degrees, ideally would be even below 1.5 degrees. So this would be very much the most optimistic scenario. Then the rate of glacier increases even more. So by 60% or up to even 80% in a close to 3 degrees scenario. What we see also in this graph is that we have very strong differences in sea level rise rates, which is each year glaciers are going to contribute to sea level rise, and the steeper this curve, the more we are going to raise sea level each year because of the melt of mountain glaciers. So what I'm going to try to do now is to classify these scenarios in a bit more quantitative way. So what we are going to do is, yeah, I've said this already. So we are going to lose at least 25% of total glacier ice no matter what, and probably even 40% by 2300 it should be, not 2100. So what we are going to do now is we are going to classify these scenarios a bit in a more clever way. We are going to ask, okay, what's the state of mountain glaciers in 2100? What's the state of mountain glaciers in 2300? according to the scenarios. So this is a plot which is a little bit complicated, but I can pitch through it. On the x-axis, we have one of the most important variables, which is when are we going to start reducing our emissions. And there are characteristics which are not displayed here, but which are telling, okay, at which rate we are going to decrease our emissions. Maybe I'm going to add the second plot so that you have a legend as well. And this is in 2100 and in 2300. We see many, many things in this graph. First of all is that even if we stop in 2020, there is some small difference between the different scenarios. Of course, if we are quick in reducing our emissions, we have less warming and less glacier melts. But what we see is that regardless, if we look into 2100 or 2300, more or less we have a linear increase with all other things kept constant. We have a linear increase of global glacier loss according to the date at which we have our peak emissions. And so this leads me to one of the main message of our study, which is to say that in addition to what is lost anyway, each year of delay in climate mitigation inside the emission is going to cost an additional 1% of global glacier volume by 2300. And each additional year that we are waiting is going to raise the sea level by 1.6 millimeter in 2100 and almost 3 millimeter in 2300. It doesn't sound like a lot, but it's a high cost to pay if we know how much ice there is on the globe and how much ice this represents actually. With this graph, we can also do other exercises. For example, we know that we are going to have to adapt to sea level rise. Glaciers is one of the components of this sea level rise. And we say, okay, let's say we are trying to adapt to a certain threshold of arbitrary heat, 100 millimeter sea level rise, which is about 30% of global glacier loss. We can ask the question, okay, when is this going to happen? And here again, we see a very strong dependence to the year at which we start acting on climate change and the year and how much time we have to actually adapt to such a situation. And we see that if we wait until 2050, then it doesn't matter anymore because this threshold is going to be reached by 2080 anyway. And it's an arbitrary threshold, but I think that in your mind, you can kind of imagine the similar happening for other thresholds later. In some scenarios, in some thresholds, we're actually never going to be able to reach them. For example, 50% of glacier change. Some scenarios are not even allowing us to reach this threshold. So again, here the message is very clear that the earlier we act, the more time we have to adapt to future glacier change. So even if glacier change is going to happen anyway, it makes a big difference if we start reducing our emissions now because glaciers are going to melt less quickly and give us more time to adapt to these changes. Another variable which is often part of the political discourse is to ask, to say when are we going to reach net zero CO2 or net zero greenhouse gas. So all the countries actually in their pledges, they say we are going to reach net zero by 2050. So which would be here on the left on this plot is when net zero 50 is reached. But often they don't really say how they are going to reach it. And they are going to have then quick response or slow response. We hope for a quick response, but it's more likely that it's going to be a bit later and also with different responses. And so what this graph shows is that let's say we are reaching net zero by 2180. So this is a true net zero greenhouse gas. Then in this case, we still have different outcomes depending on whether we act early or we act late. And the reason is that what actually matters for Glacier is not when we reach net zero. What actually matters for Glacier is how much we emit in total. So this is the second most important graph I would like to discuss with you today is since we now have this whole model chain telling us, okay, our emissions today are going to raise global temperature and are going to melt ice, we can then compute how much ice is going to be lost as a function of our total emission of CO2. And these align almost perfectly, but they don't form a line. what what we see is that glacier ice lost as a function of our emissions is actually flattening the more we emit. And this has nothing to do with complex physics or nonlinear responses of glaciers. It has simply to do with the fact that glaciers are a finite resource. We have that much ice that we can melt. And then, given a certain point, if we continue to emit and warm the climate system, there is simply not ice anymore that we can melt. And so this is why the curve is actually flattening. So we can take one very important message also from this graph is that if we look at this curve here, we can actually compute, by computing the slope of this curve, we can compute the cost of our emissions in kilogram of ice. 1 kilogram of CO2 emitted today will lead to the eventual melt in 2300 of 16.5 kilogram of ice, of mountain glacier ice worldwide. And the flattening of the curve I was talking about can be also translated into a cost. But this message here is a little bit different. It tells us that if we act too late, then each kilogram of ice that we are emitting impact on ice melt because ice disappeared already. So another way to put it, a more positive way, instead of saying, yeah, our emissions are actually leading to glacier loss, a more positive way to put it is to say that each kilogram of CO2 which stays in the ground now has the potential to save 16 kilograms of ice by 2300. If we continue our emissions unabated until 2050 and we start reducing emissions in panic because other elements of the climate system are going to react anyway, and it's going to be a world which I don't want to be a part of, the ice saving potentials of our emission is halved to 8 kilograms instead of 16. You might wonder maybe, where is this ice going to be saved? Because this is a little bit like an abstract terms. Okay, I emit 1 kilogram of CO2, 16 kilograms of ice are going to melt eventually by 2300. Well, we can also compute where this ice is going to be saved. And of course, as an emitter, you cannot choose where you want this ice to be melted eventually. And it depends on the volume of ice in each specific region and on the response time of glaciers. And what this graph shows is that from this 16 kilogram of ice, 0.006 is going to be actually melting in the Alps, and 1.15 kilogram is going to melt in the ice of high mountain Asia. The big bulk of these 16 kilograms are going to be melting in Antarctica and the Arctic. Another way to put it, which actually I prefer, if we keep 1 kilogram of CO2 in the ground, then we save a little bit of ice everywhere on the globe. A last question I would like to address before I finish now, it's being a very long conference and a lot of similar messages, and I'm adding only a small droplet to the sea of arguments for a more sustainable world and a world where we emit no CO2 at all. Another argument I could add is that maybe some very positive-minded people here are thinking, okay, yeah, maybe we're not going to reach 1.5, but maybe we will overshoot and then cool our temperatures again with technological solutions such as direct carbon removal from the atmosphere. And then in this case, we have seen in very stringent scenarios that we might cool the Earth system a little bit. Well, in this case, we might save a little bit of ice, but the news are grim because we are not going to save a lot. So if we look at the Alps, for example, so Central Europe, we see here the difference between the scenarios where we are stabilizing and the scenarios where we are cooling. And the difference we are talking about is a few percent of glacier ice. It might be surprising that glaciers are able to melt so quickly and recover only so slowly. The reason is that there is a very simple physical limit on how much ice we can add to glaciers every year, and this is how much precipitation will fall in the future. And our scenarios here are simplified, and we don't know how precipitation is going to change. But in a world which is cooling a little bit, precipitation are unlikely to change by large amounts. And so each year we can only add that much add ice to our glaciers, while in a world which is warming at the pace it is right now, ice is melting way, way faster than it can recover. So the Alps are not looking good. High mountain Asia, as a big icy region, you can see a very big difference in the outcome. Here also the recovering is actually not very strong, but since we have so much ice left to save in these regions, the differences between the scenarios are enormous. Here we are talking about, we still have in our hands, so to say, about saving almost the entirety of the ice in high mountain Asia by 2300, or only having 10 or 20% of ice left in high mountain Asia, just by the emissions which are occurring now. So often in glaciology, we say glaciers are melting already, and I've started my presentation by saying that 30% of ice is going to melt anyway. Well, this 30% is not everywhere, and high mountain Asia in one of these regions where we can really, really make a difference with our future emissions. Antarctica, however, has a very slow pacing responding region with a lot of ice. So this is not the Antarctic ice sheet, but the peripheral Antarctica. Here, the differences are smaller because here glaciers need a very long time to recover. And the positive effect of a cooler world and of getting back to pre-industrial emissions is going to be seen much, much later, even after 2300. So with this now, I would like to leave you here and remind you what we have done here. So we have a synthetic climate, which is hypothetical, but which helps us somehow to have a view into the future. What happens when we stop our emissions now or in 30 or 35 years of time? And there is still time to change our course. That each kilogram of CO2 that stays into the ground has the potential to save several kilograms of glacier ice worldwide. And it's better if we act now than if we act in 2050 only. So with this, I would like to conclude now, and thank you for staying at this very late time in the day. Thank you very much. I'm happy to answer questions if you have some. Thank you. We can stop.